Eu queria... Obrigada, Saulo. Eu queria só dar uns recados iniciais. Aos alunos da graduação, a gente vai ter uma sequência aí de 3 checkpoints, né, para poder contabilizar as horas complementares, tá? Aí o professor Saulo vai estar aí passando para vocês no chat os links, tá? Então, é só acompanhar para poder contabilizar as horas. O primeiro recado aqui em relação à pós-graduação, a gente está com o processo seletivo aberto, né, para inscrição aí. Então, quem tiver interesse, as inscrições estão abertas até 17 de janeiro. E if we have any... Sorry, eu vou falar tudo em português, acho que melhor aí, Cristiano, depois qualquer coisa a gente complementa depois. Na próxima semana, a gente vai ter a apresentação aí, vai ter um bate-papo sobre as oportunidades na pós-graduação, tá? Tanto no mestrado, doutorado, isso é voltado para os alunos aí da graduação que tiver dúvida, interesse. A gente vai estar explicando um pouquinho sobre o processo seletivo, as linhas de pesquisa, né? E também a possibilidade de bolsas, como que funciona aí no ingresso para o mestrado. Outro recado importante, a gente já tem aí agendado a próxima live, né, daqui a 2 semanas. Vamos estar recebendo aí o professor Zipei Sun, no dia 4 de novembro, às 4 horas. Okay, so today we have we would like to thank Professor Mauricio Terrones to present your research, and I believe Cristiano de Matos can do the introduction about the professor and his presentation.
Okay, so welcome everyone. It is our greatest pleasure to welcome today Professor Mauricio Terrones from Penn State University. Professor Terrones will talk about his work on defects in 2D metal dichalcogenides, doping alloys, vacancies, and their effects in optical emission, magnetism, electronics, catalysis, and bioapplications. So Professor Terrones is well known for everyone in the materials community. He has a very extensive bio. I'll just summarize some of the main points here. He has co-authored more than 600 publications in international journals. He has more than 70,000 citations. He has been awarded several prizes, such as the Alexander von Humboldt Fellowship, the Mexican National Prize for Chemistry, the Javed Husain Prize, the Albert Einstein Medal from UNESCO, and the TWAS Prize in Engineering Physics for his contributions in the field of carbon-based nanomaterials. He is the editor-in-chief for the Carbon Journal, and he is currently associated editor for 2D materials and Nature Scientific Reports. He works on two-dimensional materials for a long time, and mainly on 1 and 2 dimensions, ranging from carbon nanotubes, graphene nanoribbons, boron nitride, chalcogenide monolayers, and his group concentrates on the challenging synthesis of novel nanoscale materials, 1D and 2D, with unprecedented physico-chemical properties. So Professor Terrones, it's again a great pleasure to receive you at our university, even if it's a virtual visit, and the word is yours.
Thank you. Can you see the presentation or not?
Yes, it's not in presentation mode, right? Yeah, okay.
Can you see it now? Okay.
Yes, yes.
Okay, good. Well, thank you very much, Cristiano, and it's a pleasure to be with you. I mean, remotely. I hope that sometime in the future we can meet in person. But yeah, that's hopefully soon. But yeah, I think it's now we're getting used to Zoom teleconferences, although sometimes it's better to have them in person. But let me give you an update of the things that we're doing in the group and some of the work, recent work from last year and the current year that we have been doing related to 2D materials. So I will concentrate on 2D materials. I will not talk about carbon materials. Maybe that's for another occasion. Since I'm editor-in-chief of the journal Carbon, I think, at some point I can talk about carbon, but this time it will be non-carbon, right? So don't get afraid if you see I'm the editor-in-chief of the journal Carbon. I don't show carbon. It's because I have other stuff that I can talk about later. So these are the group members. So one thing that's it's characteristic in the group here is that we have students and postdocs from different disciplines, and that's something that I like. So we have physicists, chemists, material scientists, right? Basically, we're doing a little bit of biology as well, but yeah, I don't know much anyway. But that's a nice group of people, and actually when they have to work together, they have to communicate with each other in the same language. And sometimes a chemist can say the same thing in a different way to a physicist, but how do they communicate? And I think this is nice. And when they have a common goal, they discuss and they have different approaches, but sometimes it moves science faster. So these are group photos from last year's. That was before the pandemic, and this was the last photo before the pandemic. And here's the Nittany Lion that you see here. And you have the different group members. So we have, as I mentioned, we have different, these are the group members that we have, some students that have left, some students that are still here, but we have also research associates, visiting scientists, and PhD students. So it's a nice group of people, and these guys are the ones that do the job and get all things worked out. And I'm doing the presentations, but that's a nice group. So I will talk about some of the work that we started in 2012, and there was a big project, right? So that was given, so it was $7.5 million to these people, like led by a giant at Rice University, and we were part of really pushing forward 2D materials beyond graphene. When things started. So we started moving the field into the materials with the chalcogenide, the synthesis, and finding new things. And those were very exciting moments. So I will talk about some of the work related to that, but also some of the products that happened from there. So with the chalcogenides, you have all these. So basically, this is what we call this a monolayer of a chalcogenide, but it's in principle, there are 3 layers. So you have a metal layer here, and is sandwiched by a chalcogen atom. So it could be sulfur, selenium, tellurium, right? So it's having a sandwich, right? So you have the bread on top and bottom, and you have the ham or cheese in the middle. And this is one monolayer. These are van der Waals forces that keep the layers together, but you can exfoliate, and then you can get many interesting properties when you go to the monolayer regime. So just as a sort of introduction, so this is a work that was done by Kim-Fai Mak and in Tony Hines' group in 2010, and they exfoliated molybdisulfide, and they say, well, there's a monolayer here, and there are 2 layers here, and when they had the monolayer, you have this huge photo PL signal here, right? So which is related to a direct band gap. So what happens in the band structure is that when you have the bulk, you usually have an indirect band gap. This is the K point. So you usually have an indirect band gap. As you start reducing the number of layers, this indirect band gap becomes larger and larger until the direct band gap at the K point becomes the shortest one. So that means you have a transition here, and you have a direct band gap here, and then you have this PL signal coming from the monolayer. And that's something that's beautiful in these systems that are semiconducting. And then you can see easily a monolayer compared to 2 layers or 3 layers. So this is what's very, very important. And we are now growing monolayers of all these different systems that are semiconducting. I mean, there are also metallic phases. I will not talk about those, but I will talk about the semiconducting ones. And what we do now is we introduce defects in a controlled way. So in order to see how the properties change and how we can tune properties, right? So, and this is what I will talk about today. So we call this defect engineering, and I will classify the defects by dimensionality. I mean, people can classify them in different ways. So I would call these zero-dimensional defects, so like point defects. And you can have vacancies here. So if you remove metal atoms or chalcogen atoms, you have vacancies here. You can have also odd atoms, right? Or you can have functional groups here as well. You can also have substitutional doping. So if I exchange one of the chalcogen atoms or one of the metal atoms, you can also exchange those, and then I call this doping. You can also introduce structural defects, like this is like a square-like feature or an octagon-like feature. And when you introduce these ones in the lattice, you start to get positive curvature, and then you start closing, right? So like a Fullering cap, right? So it's like a nanotube cap. And here the octagon provides some sort of negative curvature to the structure, but these are, let's call it zero-dimensional defects. And you have the one-dimensional defects, which are the edges of these structures that can be passivated or functionalized, but the edges are very active. You also have grain boundaries. For example, you can have this octagon square sort of grain boundary in this chalcogenide monolayers, or you can have in-plane heterostructures. So you can stitch together a moly sulfide with a tungsten sulfide monolayer, and they're in the same plane, and you have these one-dimensional channels. So here you have all these one-dimensional channels, which are very interesting as well from the physics point of view. Then you have what we call the two-dimensional systems or two-dimensional defects, which we call this stacking, right? So you can have van der Waals solids, or you also have moire. Folding, so the layer can be folded and you can apply some strain here, or you can have scrolling or rippling into of the 2D monolayer. So these are the possibilities of defects, and some of the work that we have done, it's related to this, right? So how can we introduce different dopants? How can we introduce or control the number of vacancies? And what are the properties, or what are the changes in the properties? So let me just go and explain some of the recent work that we have been doing with substitutional doping, right? So let's concentrate on that one. And this is just a method that we published last year, but it's sort of a universal method that we published. So in this case, we say, in principle, you could dope with any element your monolayers of tungsten or moly sulfide, or moly selenide and tungsten selenide. The way to do it is that you use a liquid phase precursor, right? So usually it could be an organometallic compound, and that would be your dopant here. And you will also have, in this liquid phase precursor, you will have also the moly or tungsten atoms here. So you spin coat, you put here your substrate, you put your sulfur chalcogen powder, could be selenium or tellurium powder. And then what you end up having is you can have doped chalcogenide. So this is an example of a moly sulfide, tungsten sulfide, so interface. So you have in the center, you have moly sulfide rich. In the outside, you have a tungsten sulfide rich. And then in the middle, you have sort of vanadium as well, doping this structure. So what you see here, it's at the edge, this is the Raman, right, of the tungsten rich. So we have these two signals from the tungsten disulfide. You have in the middle, the combination of both. And then in the center, you have mainly moly sulfide. And then you have the vanadium atoms that are these ones in blue. So these are very rich systems. It's just to show you the things that we can do. We can also do it with rhenium. So we can dope with rhenium. Again, rhenium disulfide rhenium dope molybdisulfide. And sometimes when we do the right things, we have this hetero interface, one in-plane hetero interface of 1T prime rhenium sulfide with the 1H hexagonal semiconducting moly sulfide with the rhenium sulfide. So this is nice. And here we can see the dopant, right? So you know, shining more than the other ones by the Z contrast. So we can, in principle, just dope with any element if you do the right chemistry. But this is a very general way of making these beautiful triangles. And actually, it's very simple, right? So. But now what we want to do is make things easy so people can make samples in an easy way. So we can advance quicker with in the science of these materials. So let me just go and show you the work that we have done with vanadium. I just gave you some examples and these are good examples. But so what did we do with the vanadium? So we used the vanadium precursor. This is vanadium sulfate here. And then we used our tungsten precursor, which is this one. So we spin coat it, and then we use sulfur powder, we vaporize it. And what we ended up having, it's a vanadium doped system that vanadium is, you have the tungsten sulfide lattice, and then you have vanadium dopants here. And then we can see the vanadium by yields. And I will show you the transmission stem images, the scanning transmission electron microscopy images. So this is a pristine material. This is when we have 0.4 atomic percent of vanadium. So they look like vacancies, but they are not vacancies. There's an atom in between in there. And then you have 2% or 8%. So 8% it's quite a bit, right? So when you do a line scan here, you can see the vanadium atom is there. Very low intensity, and when here you have two vanadiums, one here, one there, and then you have one sulfur vacancy here. So we can see these defects by electron microscopy, and then we can have an idea of the density of these dopants. So this is important because putting this large amount of vanadium into the system, it's very complicated. It's very difficult. I think maybe we're the first ones to achieve 8%, and we can go to 12%. But what do you see when you control the vanadium concentration, and then what are the properties that change? So the first thing we can do is Raman spectroscopy. And again, this is the pristine one. It's the black one. Then you have the lightly doped, remember it's 0.2. Then the other one is 2% and 8%. So then you have the E mode, the E prime mode, which is the in-plane mode, and the A1 prime, which is the out-of-plane mode. So the chalcogen atoms move in this direction. Another one is just the mode that is in the lattice, right? So one thing we noted for when we use the green laser is that as soon as we start putting some vanadium, this resonant peak, which is the E prime mode, starts decreasing in intensity. So that means we are really affecting the lattice. So the in-plane vibration it's been affected, and the signal, and the ratio of these two peaks, it's also affected. And then we can see the LA mode, and then you can see another sort of peak coming here from the defects. So one thing that we see again, it's from the pristine, you have this direct band gap, as I explained. As you start doping it, you can see the shift in the direct band gap, so to lower energy. So you are reducing the band gap as you increase the concentration of vanadium. So this is the first thing we observed. And the nice thing about this system is that when you measure transport, you start to see the changes in the electrical transport. So it's an N-type semiconductor, and as you can see, this is the N branch of the semiconductor, and these are different devices that were made. So as we start introducing vanadium, we can see that the P branch starts developing. So you start to have a P branch and bipolar behavior, which is very interesting. And then when you have it heavily doped, then you have this nice bipolar behavior. So again, this is nice. So we start changing the transport properties. We see that the structural properties also change. But to our surprise, then we could still start seeing some ferromagnetism here. So it was, this is the ferromagnetism. It was interesting because we saw the most intense ferromagnetism when we had medium dopant, right? So this is a diamagnetic signal, right, that we are recording. We are not subtracting anything because we want to see the signal as it is. And then when you have 0.4, you have a little bit of this hysteresis loop. When you have 2%, you have increased here the ferromagnetic signal. And when you put 8%, it sort of decays again. So, so something is happening, right? So you are doping with vanadium atoms, and then when you are applying a magnetic field, you are magnetizing, and the spins can go in one direction or the other direction if they are far away. As you start to bring them together, if they can basically, they interact with each other, and then becomes, you have an antiferromagnetic sort of pair. And that's what happens when you have so many vanadiums close together. They cancel each other because you have these antiferromagnetic systems. When they are far away, still you can see the ferromagnetic signal. So that was very interesting because you can see this as a function of the amount of vanadium that you are incorporating. So the other thing that we see here is that, well, this is the calculation or extrapolation of the Curie temperature. So we estimated that it was around 400. So it was above room temperature. So if you see the magnetic coerce or the coercive fields at room temperature, they were around 130 oysters, and at low temperatures they were high, but 180. That was tungsten disulfide. So we have been collaborating with the Vin Crespi's group doing the theory, and here one thing is clear. So when you have just one single vanadium atom in the lattice, this is the spin density of states, and basically you can see a little bit of ferromagnetic signal. But when you have the two vanadium atoms and they are far enough far away, you can see again the ferromagnetic contributions happening here. And there are other configurations here that you don't see ferromagnetism. So it depends how close or how far you have these vanadium atoms. I think this is very, very important, and we have done this with tungsten disulfide, and we have done this we have observed this with tungsten diselenide with 4%, and this is, we did it in a different furnace, actually different process that we were making this vanadium doped tungsten disulfide. Also, we did it with vanadium doped tungsten diselenide, and the nice thing again in the this is for tungsten diselenide is that the coercive fields, right, at room temperature are much higher than the tungsten disulfide. So this is very interesting material, and we can see that it happened with tungsten disulfide, tungsten diselenide, and we have a couple of papers on this. So this is a nice way to change the properties of the material. And I just showed you, okay, can you control the amount and the dopant, and then you can control the properties. Let me just move again to another system that we have, and this is the, let's say, carburization of the TMD. So let's try to dope it with carbon. So people say, well, that's impossible to dope it with carbon. And then, well, there's some previous work that people have tried to dope it with nitrogen, and some people that they put it too much carbon that they got graphene, right? So but that's fine. So what we did is we grow the tungsten disulfide monolayers. You have this, right? And then after growth, we do a plasma treatment at high temperatures with methane. So we're trying to create some vacancies of the sulfur and then see if we can replace some carbon-hydrogen bonds that can replace this, can be inserted into these sulfur vacancies. So this is the result of the PL. Well, let's go to the Raman first. So this is a pristine material. I showed you the tungsten disulfide with the vanadium case. And this is the amount, the flow rate of carbon of methane here. As we introduce more carbon, we can see that the E prime it's again reducing in intensity. So the ratio is changed compared to the A1 prime. And this is when you have more carbon into the system. What is happening as well is that the gap is changing. So you again reduce the band gap, and then we get this hump, which could be related to defects. So just to show you what happens, it's if we don't put any methane, you don't see these shifts. So this is on treated sample. This is just by heating it, and there's no plasma. You just heat the sample, nothing happens. If you use the plasma with argon and no methane, then this is what happens. But you don't see this behavior of the peaks. So again, this is something that we try to confirm. So with the Susan Sinnott's group, then we said, okay, what are the possibilities that we can find? I mean, can we find some carbon? But carbon is substituting the carbon instead of the sulfur vacancy. That's very energetically not very favorable. And what is more favorable is when you have this negative energy. So it's the carbon hydrogen. So you have a carbon hydrogen unit. It's more stable that it sits this in the sulfur vacancy, or even the CH2 unit as well is sort of similar in the stability. So we have done some work on this, so this is, again, this is the carbon hydrogen, this is the carbon and two hydrogens, and this is the just having the carbon on top, right? And this is the most stable one. And you can see when you do this one, the band gap is reduced here. So at the K point, and this is something that we could see in the experiment. So if you remember, we could reduce the band gap by a factor, and this reduction can be explained here. So then you have contribution of the carbon, right? Of the carbon atoms here in the valence band. And so what do we see in electron microscopy? So in electron microscopy, we see this is a sulfur vacancy, but I mean, maybe you don't see it, but the sulfur vacancy is there. So there's one sulfur missing. And this is the replacement of the sulfur vacancy by a CH group, right? And this is the line scan. So when you do a line scan, this is experimental. When you do a line scan, you have the vacancy of sulfur, it's like this. And when you see the CH at the vacancy, you see this pattern. So you can see there's a mild difference, and we can differentiate the CH groups with the normal vacancies. So this could be observed as well in the electron microscope. And again, this is very interesting because with Saptarshida's group, we first found that if we had a dope with carbon, at some point we could see an unbipolar behavior. Again, remember the tungsten disulfide it's N-type. And if we just do the plasma treatment without methane, nothing happens. You don't see this unbipolar behavior. So this is related to the introduction of carbon. So can we introduce carbon in different concentrations? And this is the answer is yes. So you have an N-type semiconductor, the tungsten disulfide here. And as you introduce more carbon, again, you start to see the P branch developing until this becomes a P-type. So this is very interesting, right? So you introduce more and more carbon, and you completely change the electronic behavior. So this is another way of looking at the doping. And again, they are very different. You look at the periodic table, and then you start thinking about what else you can put in. And I think it would be interesting to look at those. So, I mean, there are different ways, different dimensionalities and of defects. But what I wanted to show here is that sometimes you have these lateral heterostructures with tungsten and moly sulfide that I showed. And you have these interfaces, or you have this sort of system with sort of like atomic stripping. So you have stripes of moly or tungsten in the system. So, but when you try to hit these monolayers, and you have an alloy of tungsten and moly, are these more stable, right? Or what happens to them? So one thing that I think is important to look, and this is something we did, some experiments we did with this structure. So the outside, it's So this is the triangle. This is how we heated this triangle. The outside of this triangle is rich in tungsten. The inside it's rich in moly, and you have an intermediate phase. So you can see low moly. So that's the edge. So the moly atoms are this. They look like darker spots. The intermediate phase, we have tungsten and moly. What you can see, the bright and darker spots, that's moly and tungsten. And when you have a high ratio of tungsten and of moly, you can see lots of the darker spots are also dominating there. So this is like having an alloy like 50-50, right? Or intermediate is like you have more tungsten here, but here you have tungsten and moly. So what happens when you heat it at 400 degrees? So you can see the electron beam starts, you have clusters forming, and the electron beam starts creating these openings of the clusters, but you can see it's more difficult to make these holes propagating when you have a 50-50 alloy. So that means that when you have an alloy in 2 dimensions, it's also very stable, I mean, towards the electron beam and maybe mechanically as well. So I think it's worth trying to study alloys in 2 dimensions. And I think this is just one example, but I think we would like to do some more work along this direction. So let's try to have some, well, I call these Moar patterns, but you will see why I'm calling this Moar, because the Moar also, when you have 2 hexagonal lattices or 1 hexagonal, but 2 periodic lattices, when you start twisting them, you start to have interesting patterns. And 2 hexagonal ones, you have this Moar. So one thing that we tried to do, and we submitted a proposal that I thought it was impossible. We sort of said, okay, let's try to make some hetero interfaces of moly carbide and moly sulfide, although the moly carbide, it's a bulk material, it's not a layer material, then the moly sulfide it's a layer material. So can you make these hetero interfaces or vertical, and that was something that we were wondering, but the way to do it is you can use a templated method. So in this case, there's some paper already that they made this alpha moly carbide flakes. So it's easy to make. So basically you have a moly film and you add some copper foils as well. And then you flow methane, right? And then you can do it like stacking the moly and copper foils like this or like this. And then when you end up having, it's these beautiful, very thin crystals of moly carbide. So these are hexagonal or triangular crystals of moly carbide. You have this sort of striping, which are stacking folds, but here you can see the thickness of these crystals, let's say it's like 20 nanometers, very thin. Again, this is bulk. And you have beautiful patterns. So this alpha moly carbide is superconductor, but you can make these beautiful crystals. So now the idea is that can we transform these crystals or partially transform these crystals into moly sulfide? And this is what we did. So what we did is sulfurization with H2S gas or sulfur powder as well. So you have the pristine hexagon here, platelet, and then after you sulfurize it, you see the hexagonal is preserved, but then when you do STM, this is the alpha moly carbide, and when you do the STM, you see a sort of Moar pattern here, which is, I will tell you what that is, but it's the stacking of the moly sulfide with the moly carbide. So after 5 minutes sulfurization in the XRD, you start to see the moly sulfide coming and the gamma prime and gamma moly carbide, besides the alpha moly carbide. So you start to see new phases of the moly carbide. And that's quite interesting. Then you have the Raman, so you see the moly sulfide, right? And then by XPS we can see the moly oxide, moly carbide, and moly sulfide as well as the moly oxide peaks. So this is the Moar pattern that we believe is happening is that you have exactly the hexagons are eclipsing each other, but they are of different sizes. So the moly sulfide hexagons are different from the continuous moly carbide hexagons. And this is the pattern that we see. This is the 2 patterns that are overlapped theoretically. This is the overlapping of both, and this is experimental one. So this is a good overlap. So what do we see in this system? So Here is the platelets of molycarbide, the alpha molycarbide. Again, you have this beautiful hexagonal pattern, and then everything you can index, and you have a beautiful face of this. So what happens when we start just 1 minute sulfurization? This is very interesting because we start to see in the diffraction pattern, you have two families of rings. So you have one inner ring and one outer ring. So that means that you have two phases, right? So, and in this case, we have the alpha molycarbide, one of them like this, and then you have the gamma prime molycarbide. Gamma prime, it's a strained phase of molycarbide. And what you see here is that you have these sort of layered structures, and one of them is the gamma prime molycarbide, and then you start to see the alpha molycarbide. So we start from the edges, we start with the sulfur, the H2S helps us to start transforming the alpha molycarbide into strain phase of gamma prime molycarbide. And then you don't have any molysulfide growth yet. After 5 minutes, you can start seeing some molysulfide here, and then you start seeing again, you have here 3 rings, right? Which tells you you have the alpha molycarbide, you have the gamma prime molycarbide, and you have the molysulfide. So you have all of them coexisting. So you have a sandwich heterostructure of having all this. And when you do it for 20 minutes, then you have, again, now you have 2 peaks, and then you have the gamma molycarbide, which is the most stable one. So you transform your alpha molycarbide into gamma molycarbide, and then you have this molysulfide as well. So this is very nice. And then what is interesting here is that this 1 minute, this metastable sort of state is very interesting. I will show you why. So this is an illustration. So you have all molycarbide. After 1 minute, you have gamma prime molycarbide and alpha molycarbide. You can see the layers. And then after 5 minutes, you have molysulfide, and sometimes you have molysulfide layers in between. And then you get this system, which is mainly gamma molycarbide. So this is what we have seen. So what happens is that the carbide starts being transformed from the edges, and the H2S, you have stacking folds, and the H2S diffuses very rapidly along these stacking folds, and that starts transforming the molycarbide into molysulfide. But before that, it creates a sort of monolayer of gamma prime molycarbide. So one thing that we looked at is the superconductivity here. And this is a superconducting transition of the molycarbide flakes that we make. So beautiful, very sharp transition. That means it's a very pure system, very pure phase. But then instead of 4 Kelvin, when we have the 1 minute, we start to see an increase in the TC to 6.5, close to 7. So we increase the TC just by having this sort of system which has gamma prime and alpha molycarbide. When you have a little bit of molysulfide as well, and the gamma prime and gamma, it's again the TC, it's increasing, and you have the other sort of steps which could be the transitions of the other phases. And when you do the 20 minutes, the system is it's a good metal. So we couldn't see down to 2 Kelvin. We couldn't see superconducting transition. It might be that at very low temperature you can have this superconductivity, but again, you have a good metal. So the system transforms into something that is still metallic and is dominated by having the gamma molycarbide and the molysulfide. So the way this is happening, again, when you have the stacking folds, you have the H2S system. And we first start transforming with the sulfur, we start transforming and straining this alpha molycarbide into gamma prime molycarbide, and we start getting some monolayers of molysulfide. And then we transform this phase into gamma. So this is some transformations that go through, but I think this stacking of different layered systems, it's very neat. So this is something that we're working on with other systems, and hopefully we can move forward. Okay, so how are we doing with time, Cristiano? So
I think you can have some 20 minutes more.
Okay, so that's fine. Okay. So let's go back to the defects and let's see what else we can do with defects, right? So let's have some vacancies. Now I played with the dopants. Now we have these hetero interfaces, which are carbide and sulfides. And now this is some work of what is, when you create vacancies, can you, for instance, make these vacancies shine, right? And this is something that we know we did it. So we did it with Victor Caroso, who's is Brazilian as well. So he was here for postdoc for a couple of years. And so this is again tungsten sulfide. You have the monolayer. And this is the photoluminescence, right, of the neutral exciton. That's the neutral exciton. That's the one that I showed you in my first slide when you have the direct band gap. So this neutral exciton is the X0, and this is at 77 Kelvin. So one thing we noted is that the neutral exciton, if you map the neutral exciton, it's all this triangle. But if there's a second peak at this temperature, which we call this is a bound exciton. So it, and that happens 300 milli-electron volts below the neutral exciton. And this one can be localized on the outside of the triangle. So this, when you do the mapping of this one, you can see that this is on the outside. You can see this neutral exciton is on the outside of the triangle. This, neutral exciton is in the inside, and this bound exciton is on the outside. So you can see clearly here. So where is the signal coming from, right? So they are different, you know, yeah, this is the neutral exciton, this is the trion, right? And the trion is when two electrons and one hole come together, then you have 30 milli-electron volt difference, right? So in the band structure. But the bound exciton that we see is 300 milli-electron volts from this, right? So it's something different that is not the trion. So at that time, then we did some calculations with Bing Crespi, and again, when you have a sulfur vacancy, so you have a defect, you remove one sulfur. Remember, we remove the sulfur to introduce the carbon-hydrogen element. Here we have with one sulfur, and then we are basically what happens is that this vacancy induces a mid-gap state, right? So this is the valence band, the conduction band, and you have the mid-gap state introduced by the vacancy, right? And this energy, it's related to these are the 300 milli-electron volts. So we could, in this sample, right, what could be happening is on the outside of the triangle, maybe we have a larger concentration of sulfur vacancies, and that's why we see this beautiful pattern. So what we did is we just did the Raman on the same triangle. We did the microscopy on the same triangle. So we did, so for instance, you transfer this tungsten disulfide triangle on a TM grid, and then you do a spectroscopy here. So and then you do microscopy in the same regions. And then you can say, or you can look at the edge, and you can look at the center. And the center has a few vacancies. These are the sulfur vacancies. But the edge always has more sulfur vacancies. So we basically then quantify the sulfur vacancies, right? You can see that this is a sulfur vacancy. So you have, this is when you have two sulfurs, one on top, one on top and bottom. Remember that the sandwich structure. But when you have one that is gone, then you have the reduction here in the intensity, and then you have again one vacancy and then one metal vacancy as well. So we did the estimation of how many vacancies on the outside and at the edge and on the interior, and we can see that there is significant increase when you have it at the edge. So this was an easy way to show that you have excitons that at low temperature they bind to these defects, and at high temperatures they don't, right? But you can identify these bound excitons to these defects. There are other defects, there are other things, and things can get very complicated, but this is just to show you. And this is the behavior of the neutral exciton. So When you reduce the temperature, you can see the behavior of the neutral exciton. That means the center of the triangle. And this is the behavior at the edge when you have the neutral exciton behavior plus the bound exciton. You start to see all these sort of, as you reduce the temperature, this bound exciton is more, it's more noticeable. So this happens, is a thermally activated exciton, right? So you start to see it at low temperature. So one thing as well is that we can see when you use different powers of your laser, you can pump the excitons from the regions, right? In the interior, as you don't have many vacancies, as you increase the power, you don't pump any excitons. But here in the at the edge, when you start increasing the power, you start to pump excitons, and you can see this bound exciton intensity increases. So, and we can correlate this to this system, and this is related to this. This is the bound exciton, and this is the neutral exciton, right? So we can see the two excitons and the linear behavior. So this is nice work, and then you can see here, you see at low temperature, you can see the bound exciton very clear. At room temperature is not there or close. It start to happen at 90 K. So this is a nice result, I think. So one thing that we are now trying to understand as well is it's in these vacancies. So we know that the vacancies create this bound exciton, the sulfur vacancies. Now, what happens if, can we use Raman spectroscopy as a tool to estimate the number of vacancies or the proximity of these vacancies or how defective your material is? And this is something that we did in ACS Nano. We published this recently. So we use gallium ions and we radiated with different doses, and then we perform Raman spectroscopy, right? So, and then is the final crystal length. So the crystalline length from defect to defect, the average crystalline length from defect to defect is what we calculated. But you can estimate this average crystal, finite crystal length using Raman. So we ended up having a formula that people can use. So what we did is we used the pristine material. We started irradiating with gallium atoms, right? And you see that the LA mode starts appearing as the number of defects increase, and then that's sort of similar to the D band in graphene. I mean, it's different concept, but you can associate that to the defect. And again, this is what happens. So you can then plot the intensity of ratio of the LA mode with the E prime or the A1 prime, and as a function of the dose, right? So, and these are sort of linear behavior. So one of the things is that this is a pristine system. This is after ion bombardment. You can see lower mag or higher magnification. You can see how bad the sample can be, right? So basically, you irradiate and you remove lots of material. But what can you measure? So one thing we did is it's the finite crystal length. So which is this distance. We didn't do the defect distance because if the defects are too large, these two defects might get into one, and then when you try to get to work out this, you will see that the distance between a large hole to another large hole is it's maybe smaller, but that doesn't mean that you have more defects. So the way we did it is we just did what is the crystal length here from defect to defect, and we can do it with different irradiation doses. And the point here is that as you increase your irradiation dose, right? So your mean finite crystal length starts to go lower and lower and lower. So that means that you have more defects, right? And these are the formulas. So if I calculate the intensity of LA and the A1 prime, and I can get it, I can get this finite crystal length. So, or if I do it with the E prime mode. So these are the formulas that people can use, and they can estimate how defective the system is. And I think this is quite useful. So one thing that we did as well is that, okay, so once you have these defects, right, can you heal the defects of sulfur? Can you reconstruct the sulfur defects? And the answer is yes, partially. So if you do H2S annealing of this system, you are starting to fill the defects of sulfur with with the sulfur atoms, and then you sort of here you can see, right? So the anneal one, so this is the pristine, this is the photoluminescence here, and after after radiation there's almost no signal, but after annealing it sort of recovers. It doesn't come back to the same one, but it recovers somehow. Okay, so I think that's a nice thing that we can do. We have similar formula for moly disulfide, but again, this is a way to use Raman spectroscopy and get an idea of how defective the samples can be. Let me just show you the work that we have been doing with bio and cells. So you know that the monolayers, they fluoresce, right? So can you make, and this is a cell. So this is so you have these cells. Can you get these cells to ingest this material that fluoresces, and can you use it as a contrast agent for imaging cells? And this is something that we did, right? So what happens is that you basically grow your tungsten disulfide triangles. You put your cells, and then they start. You can see the cells here, right? And then you have the triangles here. And after some time, you remove the cells, right? And they have ingested the fluorescent material, and you can see that they are shining. I will show you some more imaging. So this is the material before and after the cell has ingested the triangles. So you have a nice photoluminescence, you have a nice images, but after ingestion of this of the cells, you can see there are vacancies, and these are sort of extended vacancies like triangles, right? So it's like the cells like eating Doritos, right? So that's a 30 nanometer scale bar. But and they have ingested. So one thing that we noted is that before ingestion, the cells don't fluoresce, but after 4 hours of ingestion, so you can see the cells, they shine, and after 48 hours, they keep shining. So one thing that is happening here is that the cells start to divide and replicate. And the nice thing about this is that even after 2 to 3 generations, the fluorescent material was passing from one generation to the next. And that's very interesting because you can follow maybe infections, or you can see, you can use this. We still don't know what is the ingestion mechanism of the cells, but they have really ingested this material, and they fluoresce and they pass it through generations. And I think this is different from the current particles or dyes that people are using. So this might have some implications. This is just to show you the absorption. So you have the cells before digestion, right? This is these two peaks are the A and B excitons of the tungsten disulfide. This is the fused silica. After ingestion of the cell, you see these two peaks, right, in the cell. So that means the cells has ingested the material. And then we check the cell viability. So we see, is it very harmful for this type of cells? So maybe because the cells can die, right? If they ingest something that is not good, they can die. In this case, the cells we tried, they were not making any much change, right? So the cells after ingestion are the green ones, and the cells before digestion are the red ones. So basically they are very comparable. So that means that this is a system that can be used in the future. Okay, so yeah, I have very new data that yeah, maybe I just give you a glance of what we're now doing. Some vacancies of in hexagonal boron nitride, just to give you a flavor of what we can do now. So you can introduce some vacancies in boron nitride, but boron nitride it's an insulating material. It's a ceramic. You can heat it to very high temperatures. But what we did it with cryomilling. What we did is that with cryomilling, which is basically in a nitrogen atmosphere, so you don't have the boron nitride does not react because it's a nitrogen, right? So when you take it out after cryomilling, it's sort of more reactive powder, right? So we can increase the milling time, and just to get, so with the cryomilling time, we can see that the surface area increases, right? And this is the surface area, which is like around 200 square meters per gram, and the pore volume as well. But one thing that it's interesting is that this is a boron nitride, right? So boron nitride, you don't have any PL emission, but when you start having defects, and these are different cryomilling times, you start to see these peaks that is sort of emitting from these defects. And then people have seen single photon emission. But one thing that we noted as we introduced the defects, we could see in ESR or EPR, we could see that there was this sort of unpaired electrons were due to the creation of these vacancies. And in microscopy, we can see these extended vacancies, and we can still see point vacancies on the lattice of the boron nitride. So one thing that we did, and this is just for the chemistry part of this work, is that this is the cryomilling time, so 900 minutes. And then we can see that we can reduce silver nitrate, and we can see here that you have a sort of brownish solution, and that's because you are reducing the nitrate into gold and silver nanoparticles. So when we look at the system, you can see the silver nanoparticles very, very well anchored. If you do an XRD, you see the X-rays, you can see these beautiful nanoparticles, but you can do it with gold, with iron, with copper. So we are making a system that is boron nitride that is reactive, and it can be used as a support for catalysis. And I will not get into the mechanism, but one thing that we did is we did this platinum silver that was anchored to the let me see if I have, no, it's not here. I don't know where that is. We have anchored this to the the image I wanted to show is not here, but anyway, so so we have seen the HER, right? So, and this is the Tafel slope of the boron nitride with platinum. So we can have single atoms. In the case of platinum, we have single atoms in the lattice, single atoms of platinum. In the case of silver and platinum, we have single atoms on the surface of the silver that is then anchored to the boron nitride, and this seems to be a very good catalyst, right? So, so we are improving the Tafel slope and the current, and we are making these materials as a good materials for catalysis. I think we can do many things with these systems. We have seen that the stability of these clusters with boron nitride is very high, so you can heat it at higher temperatures and the clusters remain there. So I think this could be used as a new support for catalysis. But again, and this is driven by defects, right? So you create some defects, you improve the reactivity, and then you can reduce salts and make it, make these clusters, very small clusters, or make these even single atoms of these metals. So with that, I just finished. I would like to thank our sponsors, and I would like to thank you for your attention. And if you have questions, here's my email. Thank you very much.
Thank you very much. Thank you very much, Mauricio. Excellent work. Very interesting seminar. So we have a few questions, and if you still want to make questions, use the Q&A. You will find it at the bottom of your screen, the icon Q&A. So write the question down, and I'll read it to Mauricio. So we have a question from Krishna Sampat Kuma. He asks, gamma prime phase in MO, so moly carbide from 5 minutes sulfurization is stable?
Yeah, actually, that's a very good question. That's exactly what we are doing. So basically, we are stabilizing phases in sandwich in between. So the material is very stable, but in between, we are having very highly strained phases like the gamma prime, and that you stabilize the material. So we're trying to do this to work on different carbides now, and I think you can make stable, I mean, very highly strained phases that are very reactive, but you have them in between other layers, then you have them stabilized, and you can gain from the properties of these systems. That's the point.
Okay. So Leandro Seixas, Professor Leandro Seixas asks, first he says excellent talk, and then he asks about the moly carbide, moly sulfide heterostructures. Is there any magic angle similar to those in twisted bilayer graphene?
I think that's a very good question. In this case, we're limited by the epitaxial growth, right? So we grow from the moly carbide, right? And we have the alignment of the hexagons from moly carbide and moly sulfide. They are just one on top of the other one, but one set of triangles is smaller than the other one. So when you have two different sizes of hexagons, and you overlap them, you get exactly that moire. Now, what we would like to do is, can we sort of tilt it with small angle or with large angle? And I think the properties will change. Now, experimentally, how we do it it's something we're trying to do.
So with epitaxial growth, you only get one angle.
Yeah, right? that's right.
Yeah.
So yeah, but I think it's a very interesting systems. These are very interesting systems.
Okay, I have a few questions myself regarding the bound excitons in vacancies. Do you have any results or even theoretical that gives us information? For instance, if the vacancy is made of actually not one sulfur atom vacants, but two adjacent, do you have changes in the exciton energy, or is the exciton energy affected if you have by the distance between the vacancies or something like that? My question is essentially the work you've done with Raman, right? That you can associate changes in Raman to the density of vacancies or even the shape of the vacancies. Can you do something similar with exciton PL or something like that?
Yeah, with the PL, I think this bound exciton is characteristic. If you see a bound exciton at low temperature that is 300 below your neutral exciton, that means you have sulfur vacancies. Sometimes I can tell you when you look at when you look at the PL signal, sometimes you find very broad signals. So you have convolution of the neutral exciton plus a whole family of excitons that you have no idea, right? And all these defects will be there. What is interesting is that if you are, some of them are thermally activated, so you can start seeing, when you decrease temperature, you can start seeing some and not others. But sometimes you have a convolution of many. So for instance, if you have a metal vacancy, you have other types of mid-gap states, right? So, and then you can look at those energies when you have the metal vacancies. And then sometimes those energies are in the range when you have these broad peaks, right? So, so, or when you have a dopant, again, usually with a dopant, usually the excitons are, you need a sort of vacancy or in order to have them bound. But when you have two vacancies, if they're far away, they don't see each other. If they're too close to each other, I think you have also other types of mid-gap states that maybe you will be able to see. But we are trying to finish one paper that it's a very complex excitons, because you can deconvolute in 3, 4, 5, or 6 excitons, right? So it's a broad, and then and some of these locations of the excitons have meaningless interpretation. So it's a more complex. I showed you I sort of simplify things, right? But I showed you what we know, and there are many things that we don't know. But I think it's good to. I think the PL, it's also interesting. The exciton lifetime could be another way also to estimate the defects, right? As you increase the number of defects or dopants, then you see the exciton lifetime it's shorter, right? I mean, it's longer, right? So
yeah, perhaps with a SNOM or something like that, with resolution, you could measure or characterize individual.
We have some hyperspectral work, but again, we see all these broad excitons.
Right.
A bit more complicated, but yeah, but in principle, yes, but in reality, it's...
I understand. We have a question from Professor Camila Maronesi. She asks if the density of defects for MoS2, chemically exfoliated MoS2. Sorry, let me read it because she wrote in Portuguese. Have you estimated the density of defects in chemically exfoliated MoS2 with lithium in the metallic phase?
Okay. That's an interesting. We haven't done it. We can do it, but I think that's an interesting. I think the process, it might be that you get some vacancies but we don't know the vacancy, the density. One thing we know is that the CVD growth tungsten sulfide or chalcogenide usually have a high density of sulfur vacancies, right?
Okay.
So you might need to heal the material before you do something else. But then if you use crystals, usually crystals, sometimes they have better crystallinity, but that depends who makes the crystal and how it was made. But when you exfoliate, I mean, this sort of exfoliation, because intercalation and exfoliation is sort of exothermic reaction, you might get some more defects. And that's something that we have not quantified, but you might see more defects, yeah.
Okay.
I mean, you can use the formula, the Raman formula, and then check, yeah.
Okay, I have a question regarding the vanadium doped tungsten sulfide results you showed. For vanadium, is it always anti-ferromagnetic? Is there any way to get ferromagnetism?
No, we get ferromagnetic when they are far away.
Yeah. Oh, yeah. Okay. But when we increase,
when they have interactions, then you have anti-ferromagnetic. Yeah.
Okay.
Yeah, that's when you have medium doping and sort of they are reasonable. So if they are around average distance, about 1 nanometer or 2 nanometers in between the vanadiums, that's when you have a maximum of the ferromagnetism.
Right.
You start to decrease the density. If you start increasing the density of vanadiums and decreasing the space in between vanadiums, then you have this antiferromagnetic behavior. Right.
And can you do something similar with other magnetic atoms like cobalt or something like that?
Yeah, that's I mean, with vanadium, it worked very nicely because we can dope from 0.2% to 15%, right? And then we can see all the process.
Okay.
So far, we have only been able to do that with vanadium. We can dope with iron from, let's say, 0.2 to 1.5. But sometimes we would like to do it beyond that in order to see if you have maybe antiferromagnetic contributions, right? So, but yeah, we can dope with shortened range of other elements, and we are working on that right now.
Good, very good. So I believe we've reached the end of our time. So I would like to thank again Mauricio for a very interesting talk and for spending time with us, showing results from his group. I just want to remind the audience that in 2 weeks, we're going to have the next seminar in this series. It's going to be from Aalto University in Finland. Right, so we'll see you in 2 weeks. Thank you very much for coming. Thank you, Mauricio.
Thank you. Nice seeing you. See you soon. Take care. Bye-bye.
See you. Bye-bye.
Thank you.